Welcome to this explainer, everyone. Let's just dive right in. Today, we're going straight into the fascinating and, frankly, incredibly powerful pharmacological journey of heroin. Chemically, we know it as diacetylmorphine. This is a compound that has drastically shaped medicine, society, and global public health. But today, we're looking strictly at the science. We're going to break down exactly why it behaves the way it does inside the human body, because understanding this molecule is absolutely crucial. It really demystifies how a single chemical can hold such massive sway over human biology.
So, to kick things off, we have to pose our central biological mystery. Why is heroin so much more potent and fast-acting than regular morphine? Since heroin is derived directly from morphine, what exactly gives it such a dramatically different and rapid impact on us? It's a molecular mystery for sure, but it actually holds the key to understanding both the drug's power and its extreme danger. Well, the answer comes down to a property called lipid solubility. Standard morphine crosses the blood-brain barrier relatively slowly. Heroin, however, it is highly lipid-soluble, and this chemical trait gives it a physiological VIP pass, allowing it to breeze right past the blood-brain barrier much faster than morphine ever could. It's exactly this rapid entry that sets the stage for the whole shebang.
Okay, section 1, the brain's chemical transformation.
Once the heroin molecule actually gets inside, your brain essentially acts as this highly efficient chemical factory, kicking off a super rapid sequential breakdown. Step 1, the molecule enters the central nervous system. Step 2, specialized enzymes called esterases immediately get to work. They metabolize the heroin into a compound called 6-monoacetylmorphine, which scientists just call 6-amom for short. And finally, step 3, that 6-amom is further converted into morphine. Both 6-amom and morphine are the actual active substances producing those opioid effects.
So, here is the absolutely crucial point. Heroin itself isn't actually doing the heavy lifting here. It's essentially just a highly efficient delivery vehicle. The intense, fast rush that users experience isn't from the heroin molecule activating receptors directly. It's from the incredibly rapid onset of this conversion into 6-MAM and morphine right there inside the brain. This sheer speed is exactly why heroin carries a vastly higher abuse potential compared to a lot of other opioids.
Moving on to section 2, hijacking the reward pathway.
Once the diacetylmorphine has transformed, it seeks out its primary targets, which are known as mu-opioid receptors. These are specific receptors located all throughout the brain and the spinal cord. And when the active molecules bind to and activate these receptors, the physical result is immediate and profound. We're talking massive pain relief, deep relaxation, heavy sedation, and extreme euphoria. But what's really fascinating here is the dual impact taking place simultaneously inside the brain. While that mu-opioid receptor activation is causing all that pain relief and sedation, there's a secondary, critical action going on, a massive dopamine surge. The drug literally targets the brain's deepest reward centers, specifically the ventral tegmental area and the nucleus accumbens. It triggers this absolute flood of dopamine. And it's this precise chemical hijacking of the reward pathway that drives its incredibly strong addictive potential. Which brings us to section 3, medical uses and side effects.
Now, this might surprise some of you, but there is actually a pharmaceutical grade of heroin known as diamorphine. While it's strictly illegal in many parts of the world, obviously due to its immense risk of addiction and overdose, it is important to note impartially that diamorphine is actively utilized medically in certain countries. Clinicians use it to manage severe pain, in palliative end-of-life care, and sometimes even to manage the acute pain associated with heart attacks. But as you can imagine, that medical utility walks a very, very thin line. On one hand, you have common effects like euphoria, drowsiness, nausea, vomiting, constipation, and noticeably constricted pupils. But these can rapidly tip over into incredibly dangerous, life-threatening effects, severe respiratory depression, dangerously low blood pressure, and complete loss of consciousness. It's a stark contrast, right? It just really highlights how volatile this molecule is within the human body. And here is the ultimate risk. The single most life-threatening complication of diacetylmorphine is respiratory depression. The drug physically suppresses the respiratory centers located deep down in the brainstem. It slows the body's breathing down to dangerously low levels. During an overdose situation, it's this specific brainstem suppression that actually stops the breath entirely, ultimately inducing coma or even death. Let's look at section 4, overdose, withdrawal, and antidotes. The toll of chronic, long-term use is cascading, and it is severe.
Over time, the brain requires larger and larger doses just to achieve the exact same baseline effect. This is what we call tolerance and dependence. And if a chronic user suddenly stops taking the drug, the body goes into severe withdrawal. The symptoms are just grueling: crushing anxiety, severe restlessness, deep muscle pain, intense sweating, diarrhea, and profound insomnia. It is a massive shock to the system.
But thankfully, there is a biological emergency brake, and it's called naloxone. Naloxone is a literal life-saving antidote. In the event of an overdose emergency, administering naloxone rapidly blocks those mu-opioid receptors we discussed earlier. It literally knocks the active opioid molecules right off the receptors in the brainstem, quickly reversing the respiratory depression and restoring the person's ability to breathe. It's an absolute game changer on the front lines of this crisis.
Now, beyond emergency medicine, there's also a really fascinating scientific application for investigators. In forensic toxicology, investigators don't necessarily just look for the heroin molecule itself. They specifically look for 6-MAM. Remember that chemical middle step we mapped out earlier? Because 6-MAM is entirely unique to the specific breakdown of diacetylmorphine, detecting it in toxicology reports definitively proves heroin consumption during an investigation. It's like a chemical fingerprint.
So to summarize this explainer, we really have to look at the molecule's duality. Heroin's incredibly rapid entry into the brain, thanks to that lipid solubility, and its lightning-fast conversion into active metabolites, well, it explains everything. That sheer speed is the exact mechanism driving both its limited, highly powerful therapeutic use for severe pain and the massive, devastating global public health crisis it fuels through severe neurological, respiratory, and social consequences.
I want to leave you with this final, provocative question to ponder. How will our deepening scientific understanding of these specific molecular brain pathways change the way we treat pain and successfully combat addiction in the future? By understanding the science, we take the first real step toward better solutions. Thank you so much for joining me for this explainer. Stay curious and keep learning.